Hello everyone. I think we should start on time today. So I guess the first presenter should start. Josh, do you know who's going first?
Let me pull up. I think I might be the first one to go.
Okay.
Okay, let me share my screen. Can people see it? Okay.
Yeah.
Cool. Should I go now or should I wait until the 5 minutes past 11?
I think you should start.
Okay, cool. So today I'm going to talk about visual pre-training for navigation and specifically what we can learn from random noise. So let's consider the task of visual navigation, where an agent is given a start view and a goal view and tries to figure out the actions in between to lead to the goal. One approach to do this is you can say, collect a bunch of data in an environment in the format of image sequence. And then use this image, you can train a neural network end-to-end from images to predict an action. Now, we typically want an Lstm module there to have some sort of memory component where this agent has been. With this trained up, you can use this to do inference in an autoregressive manner as shown as by the animation. There is something good about such a system, that is, it can figure out the right representation automatically through data according to the downstream task. But at the same time, there's something bad about it, that is potentially it requires a lot of interaction data that can be expensive to collect. This is because the inputs are images, high dimensional, and this latent representation typically are high dimensional as well. But we notice the action is actually low dimensional. So is there a way to actually reduce the data demand? Can we potentially pre-train this fixed feature extractor, or can we potentially also make this latent representation of the state low dimensional? To get there, let's first examine what the inputs are. The image pairs typically are of this sort of type, where the where the goal view is some sort of a crop of the current view. Now, if we have that, if we assume that, then we can use a panning angle or a tilting angle or a zooming factor to represent the relative transformation of the two views. This is very similar to how a digital camera that pan, tilt, and zoom from one view onto the other. So let's now try to use PT and Z to represent this three entry vector to represent the relative transformation of the two views. And if we replace the fixed feature extractor with this PTZ module that predicts the PT and Z, now we modified the architecture into this new sort of network. Now, if we use this, can we reduce the data need? Let's first see how we train such a module. We can, given an image, we can random crop using the parameterization PT and Z and generate two crops, and then we use that to predict the PT and Z. Because we have the ground truth PT and Z, we can use it to supervise the system. Now, if you train on training home images and then test on testing environments, the IOU is pretty high, almost perfect. And we notice if the testing environments are very different from training environments, such performance will also transfer. So now it prompts us to think, can we actually train on noise images? And then can we achieve similar performance on the natural home images? And the result is very positive. So now what that means is we can now train a PTZ completely from without any interaction data. This is good news. And let's see some inference results. If we train such a system using noise and then do the inference with only a little bit of interaction data to train an Lstm module, we get this this sort of rollouts. The first couple of images are basically exploration because you don't see the goal in your current view at all. But once you see the goal, it will basically move towards the goal. The red, it shows the bounding box where it detects in its current view the goal image. This is a video of how it performs the navigation. Okay, so let's show some results. Here, I show results from 5 environments and the 30 trajectory from each one of them. And then notice there's one thing here. The very last number at the end of the policy name means the max sequence length that you input to the Lstm. And if it's 1, that means we basically convert the Lstm into a feed-forward network. So with 2K data without the PTZ module, the performance is very low, as shown by the orange bar. If you increase the data to 30K, then the performance picked up a little bit. And then when you have 60K data, the performance is pretty good. Now, if we only use 2K data, but with PTZ, you still get pretty high performance with very, very little interaction data. And then lastly, we want to figure out maybe potentially where the performance comes from, what sort of noise is best for training the PTZ module. And then I test on 3 kinds of noise: Perlin noise, fractal noise, and shape, random shapes. And then the performance are, the Perlin and fractal are better than shape, but this is really preliminary result. My training hasn't covered yet, so I will have those in the report. With that, I end my presentation. Questions?
So where do you go next with this?
The next, I think it would be really cool if we can sort of, because right now I generate a noise with some scripted function, and then I just handpick those hyperparameters. If we can find a way to make that data generation part also differentiable, we can maybe figure out the optimal way to generate noise to do a downstream task. That would be really cool.
Okay. Now, Josh, do you have any questions?
For the exploration stage, do you use some special exploration bonus in your dual design, or just random exploration?
Over here, as you can see, it's really just random exploration. Yeah.
How well does it cover, like the coverage area in an environment by random exploration?
Random exploration has pretty good coverage. Yeah, I don't have the plot here, but I've seen that. Yeah.
Okay.
I'm curious, for the PTZ module, did you experiment with any like classical CV modules, like stuff used in optical flow rather than training a network to do it?
No, I have not, but I think that should also work well because yeah, because like the PTZ is very low dimensional, so I assume using some classical methods as the intermediate state representation can also work, because this task isn't that hard. Yeah. Yep.
I think we should move to the next presentation now. Thanks, Felix.
Yeah. Thank you.
All right. All right. You good to go, Will?
Yep.
Cool. All right. So for our final project, we looked at various methods of reducing shaky policies in invitation learning for physical systems. So there is a problem in trying to introduce machine learning to physical systems where even if a policy outputs reasonable actions, if that action changes from time step to time step, you get a output with a high frequency noise, which can be intractable to the actual physical system because motors cannot move arbitrarily quickly.
So this is basically the concept that we wish to explore in our project. The high-level overview of what it is we want to do is in imitation learning, right, the neural network tries to imitate the behavior of whatever human collected data that you have. And so what happens if that data is particularly bad, like it's not expert data, it's suboptimal in some way or another. And in particular, what we did is we generated a whole bunch of human driving data with a lot of like random shakiness, very much so not the type of driving that you would like to actually like be in when you're in that car or whatever. And then we fed it to various neural network architectures and had each of them autonomously control our simulated car to see if any of those neural networks would be particularly conducive to automatically smoothing out the like noisy learned data and thus produce a smoother policy. Yeah, so that's the idea of the project.
So for our general setup, we found a simulator that can both record data with manual driving and supports neural network integration so we can test the model. In terms of actually achieving this for the self-driving simulator, we got two data sets, one where we drove smoothly and one in which we drove in a particularly shaky manner for 5 laps each. And we evaluated each of our methods with 1 lap around this designated track.
Okay, so let's go over the policy smoothing solutions as well as neural network architectures that we ended up testing out. As a baseline, we used this small convolutional neural network, just purely feed forward, no like fancy recurrencies or like skip layers or anything like that, just 2 convolutional layers with relatively large kernels and large stride, as well as a final dropout and fully connected layer, leading into the ultimate steering angle command. Next, we tried out Nvidia's PilotNet, which is more or less the same thing, just larger, with more filters of different sizes, more fine-grained kernels, and larger fully connected layers as well. And then next up, we tried out 2 different recurrent neural network architectures. The first one is a standard one where the recurrency is just 8 dense units all connected to each other, or like to the next time step as well. And the image is sort of pre-processed by a header, which is simply 2 convolutional layers followed by a fully connected one. And lastly, we have the Lstm, which is the same thing as before, just instead of a dense connection at the recurrent stage, instead it's, well, an Lstm unit. The reason that we thought that these 2 would be particularly effective is in the event that the recurrent neural network does make decisions based off of not just the current time step, but like a small time horizon backwards, we were thinking that it might be successful in sort of naturally averaging out all of the learned data so that it doesn't produce as shaky of a policy. Moreover, we thought the Lstm might be useful due to the fact that it can forget information, which is pretty useful in driving in particular, due to the fact that when you're driving, you don't make use of information that you saw from like beyond a few seconds ago. And so that might help in addition to using like some past data, but not too much past data. Lastly, we have the moving average filter, which we use in conjunction with the small baseline convolutional neural network. This one's pretty self-explanatory. Instead of issuing the steering command at every time step, we simply average the last like n of them and then use that as the average command, or use that as the steering command instead.
So before we actually get into our evaluation.
So we have about a minute to wrap up the presentation.
Okay, yeah, I'll go through. So before we actually do our evaluation, we have to have some definition of shakiness. So here we just define shakiness over like a small, I think we use 0.1 seconds, look at time and like see how much you have to, like the slope of the line that you have to encompass that. I won't get into this too much because we don't have very much time, but all of our recurrent neural networks just failed horribly. They all fell off the track within a few seconds. However, our other methods did seem to work. As one might expect, the baseline with filter did the best, as it does smooth this high frequency shakiness effectively. Yes, sorry, I wrap it up fast. That is our presentation.
So is your action space continuous over here?
Our action space is continuous.
Yes.
It's just we output just a steering angle. We didn't really deal with throttle or anything. It's just take in 3 images from the vehicle and output the steering angle. So relatively a simple concept. And I think it's worth noting that this problem is traditionally sort of an issue in RL, but because of sort of hardware constraints of what we have in our end, we can train on. Early on, we decided to just try to induce this high frequency noise in imitation learning and solve it in that domain, which is where we why we try to produce a shaky data set.
Tao and Josh, do you have any questions? So what are you planning to do next over here?
So we have a few avenues of expansion. The first one is investigating why our recurrent neural networks did so completely trash, as in they just completely drove off of the road. I suspect that it might just be that they're not expressive enough. We're only using 8 units per recurrent cell, so that means that it doesn't have much to like actually develop like useful features to produce a control angle with, right? And also, even with the LSTM, it might still be remembering too much. And so like the state might initially be such that the car is, I don't know, asked to drive forward. And then some new embeddings come in from the images, which might suggest to like turn to the side, but then the thing still says to move forward because it's still remembering it. We might try to like have some mechanism to reduce the like time horizon that it's considering even shorter. And then lastly, the obvious avenue.
William, I just have to cut you off because we're out of time. But
Okay.
I think we got a sense of your future work. So let's move to the next team.
Okay, thank you.
Oh, can everyone see me and hear my screen? Oh, sorry, hear me and see my screen okay?
Yeah.
Cool. All of you here have done research for your final project. And you know one of the best feelings of research is finally getting your idea to work. The very natural next question, of course, is how good is my idea to compare to everyone else's? And it turns out if you're within the field of trajectory prediction or trying to determine an agent's future location given their past, this problem is really hard because very few papers actually contain code, and also some papers lack information necessary to reproduce the results. And this really shows if you look at the results section of a trajectory prediction paper, because it's very hard to know if you're beating the competition if all you know is that the competition is beating linear regression. I'm Patrick Kale, and I present my work on the Trajectory Inference Library, or TRAIL, which aims to solve this reproducibility issue in trajectory prediction by providing a baseline predictor to compare against. But before I could actually implement sort of this baseline predictor, I first had to write a lot of utility functions to get this predictor to work. And I was thinking if I'm writing these utility functions anyway, I want to focus on engineering and designing them in such a way that they can be useful to future researchers working on creating their own trajectory predictors. For the first part of my talk, I'll go over these utility functions, and after that, I'll talk about my work actually re-implementing this predictor. So machine learning is all about data. And if you want to make a researcher's life easier, you have to make sure the data process is really streamlined. So here you can see with this interface I designed, with just a few lines of code, you can create a reader, apply any transforms you want, and then also batch the training data with a custom batching function designed for trajectories. And because the interface was so carefully thought out, with just one line of code, you can swap from one data set to a completely different data set with a very arbitrary set of file formats. There were also some other utility functions that had to go into the trajectory prediction system. It turns out the problem's relatively complex. And in addition to this, I had to write some utility scripts, a visualizer so you can see the past and future trajectory of the agent, and also the data loader that I mentioned earlier. Once I had this all done, I was able to actually work on re-implementing a paper. I chose the paper Desire, even though it's a little old, from 2017, because it had a lot of ideas that were really ahead of its time. And even though this paper has like 500 citations or so, which is pretty popular, it turns out there's no online implementation of the paper that exists. So I thought this would be a great paper to choose to implement to maximize the effectiveness of TRAIL and help the most people. At a very high level, Desire is split into two halves. First, a sample generation module that generates, given an agent's past location, it generates a wide array of where that agent could go in the future. It does this by sampling random noise. The second half of the network, the refinement module, takes these sort of candidate trajectories and refines them given external scene context and also taking into account different interactions between the agents. The refinement module puts out a suggested displacement or a new trajectory, and you can feed that new trajectory back into the refinement module again and again and again until you finally get your final prediction. So in terms of how these things work, the diverse futures are generated using a conditional variational autoencoder. And because there's a fixed dimensional latent space, it turns out you need RNN encoders on one side to get into the latent space and RNN decoders on the other side to get out of the latent space and into the trajectory space. The external context is actually just a CNN feature that's sort of trained on the top-down image of the scene from the bird's eye view. And the interaction between agents are done using something called social pooling, which is like a predecessor to attention that pools the hidden states of agents depending on their relative distances. In terms of how the network's actually trained, the CVAE is trained using the very standard KLD loss and the reconstruction loss, which looks like the L2 norm computed, the L2 norm of the error computed halfway through the network, and also the final regression loss, which is just the L2 error computed at the very end of the network after both modules are done working. This trains the entire network end to end. In terms of the results after finally debugging the network for a while, you can see here that the results of my implementation are comparable to that of the original paper. The nice thing being, of course, now that they have this implementation, you can extrapolate to scenarios that were outside the actual original paper while still being assured that the results are comparable to what the original authors would have found. Here you can see a diagram of how trail affects the development process. And the takeaway here is that all the way from when you first load your training data, all the way to the very end, from after you've developed your predictor and are comparing against the baseline that I wrote, Trail aims to sort of speed up the development and research process from beginning to end. In conclusion, I present Trail, a library that solves the reproducibility problem in trajectory prediction by providing utility functions and a baseline predictor to compare against. Thank you.
Perfect. So any questions from anyone?
In your validation loss, seems like the loss is already low initially, like the, for example, where epoch equal to 5 to 60.
Yes.
Why is the initial, is FDE? Okay. Why is the distance initially, it's just low already?
So I think the final FDE stands for final displacement error, which is the distance at the very end of the trajectory. So it's like the final output versus the final output. It doesn't account for any of the intermediate behavior. And I believe this tends to be easier for the network than the average displacement error, which accounts for all the points. So this FDE doesn't care as much about the shape, but I included in this diagram because a lot of papers seem to care about this metric more, even though it seems a little easier.
I'm just wondering what happens if you take some very simple heuristic like the mean of all the trajectories of the median and just use that as a prediction.
Yeah, so I actually tried this where it outputs sort of it looks at the future trajectories and just outputs that one point, the mean of the actual future. So it even gets to cheat a little bit. And the error is actually really high. So it turns out that being able to having any neural model or anything that predicts an actual line instead of just one point repeatedly makes the average displacement error, not the final one, much better.
I mean, the surprising thing, which Tao was also suggesting, is that the error reduces by 1 pixel. Right? So it seems like, a small reduction in error, unless you're interpreting it incorrectly. So that seems like the network is not really learning much, right? I mean, it's some kind of normalization that the network learns, and that's about it.
I also think most of the learning happens between epoch 0 and 5, but this graph just clips this out. I believe that like the very first epoch there, the error is about 30, but it drops down really quickly. And then I also run the training for so long just to make sure that.
So I would encourage you. So I would encourage you in the final report, just have the full graph starting from epoch 0, and also include the training and the validation curves both.
Yeah, for sure.
Okay. Well, thanks, Patrick. I think we'll move to our next presenter.
Thank you.
Hey, everyone see?
Yeah.
Okay, great. So today I'm going to talk a little bit about my project comparing bonus-based exploration methods. If you remember from lecture, a bonus-based exploration method is just some kind of exploration algorithm that will take some extrinsic reward from the environment that can be sparse and difficult to learn from, and supplement that with some dense intrinsically generated reward signal. So there have been benchmarks and comparisons of these types of methods in the past, but the issue with these benchmarks is interpretability. Here, for example, a lot of the benchmarks will work in Atari games, and it's difficult to know why in the bottom left on Asterix, noisy networks outperforms all the other methods, whereas on Sequest, CTS seems to be doing the best. It's tough to pinpoint exactly what features of the environment lead to these performance gaps. So our project seeks to take a step back a little bit and consider these simpler grid world environments where we can design our own custom maps. We can have specific objects and isolate behaviors. And the agent here, pictured in white, can move in all four directions and has an observation window, which is just an RGB image cropped around the center agent. So here are a couple of the environments that we consider. The first is this environmental noise environment, where we have this agent here in this 5-room map that can move around. There's a fixed attractor that should always provide a source of intrinsic reward at the top by moving at the start of each episode. And in the bottom here, we have this white noise that is uncontrollable and should distract the agent. We can also measure things like task relevant features if we add an extrinsic reward. So here we have a map where, based on the color of the central room, which changes at the start of each episode, an extrinsic reward is given in one of the 4 rooms surrounding the center room. We can also add things like enemies, which give negative reward if the agent hits them. And we can measure things like prioritization, where if we have a bunch of different objects, is there a certain hierarchy or preference for each method in terms of which object they visit? Lastly, we can measure things like breadth versus depth first exploration or coverage. So we compare 3 different methods. The first is ICM, which you might remember from lecture. ICM has a forward model that seeks to make a prediction on the next state and uses the prediction error to drive exploration. We also look at disagreement, which just extends ICM using an ensemble of models. So you now have multiple forward models, and you take the variance across the predicted features as the reward signal. And lastly, we have R&D, which is a proxy for measuring counts. It's similar to ICM in that it has a predictor network, but unlike ICM, the predictor network is not a forward dynamics model. You just have this random encoding that you encode the next state with, and then you try to predict that next state's encoding. So the more times you visit ST+1, the better your prediction will get. So some results on the white noise environment. If you look at the top left, we have this video of ICM's policy. We're successfully able to ignore the white noise and visit the fixed object. In the middle here, you have all the heat maps across the entirety of training. So this is the average policy across training. And at the bottom here, we have this video of training as you explore. So that's another advantage of using the Picolab maps, is you can get these kind of qualitative metrics on how your exploration policy is looking at the space, which is not something that's possible with the Atari games. What's interesting is if we look at R&D, it has a lot of trouble ignoring the white noise. This could be because the white noise has a lot of possible states, and so a count-based method would not do as well. And if we look at disagreement, it's also able to focus on the fixed object. One key thing here is that not only does it focus on the fixed object, but it also continues to visit other rooms and focus on features like the corners, as you can see from the average heat map there in the middle. Another thing we tried was to look at coverage. So if we have these 8 rooms with fixed attractors in each room, how does our agent explore the space? Does it explore it evenly? Does it explore one room at a time? What we saw is that the agent seemed to focus on 2 or 3 of the colors. So this lime green in the top, or this cyan in the bottom left. As we looked at the videos, this was pretty consistent. And what was really important is that across seeds, so across 10 seeds, the heat maps looked the same. So they were all visiting the same rooms. ICM was always going to the top room, for example. So what this indicated to us is that object color seems to have a big effect on the exploration method. The intensity of the object will skew the exploration method into exploring one object over the other. If we change the color of the objects and make them all the same, we can now see that the heat maps are much better, much more evenly spread, and they changed much more over seed. Yeah, so a different subset was visited for each seed. One cool feature here is that ICM seems to focus a lot on the objects, so the centers of the rooms, whereas if you look at R&D and disagreement, the walls are a much more interesting feature. Another environment was the prioritization environment. Here we saw that methods like ICM, R&D, disagreement all seem to prefer this controllable object that you can push around in the top room as compared to the sources of noise in the side rooms or the fixed attractor in the bottom room. What's interesting is that methods didn't necessarily prioritize just one object. Here we see that R&D was also interested in things like the Brownian object, which is kind of an interesting case of random noise that you might have in an environment. Lastly, we also looked at whether or not the agent can overcome things like enemies. And what's interesting here is that so far what we've observed is algorithms like ICM are capable of ignoring the enemy. Here again, you get a negative extrinsic reward if you hit the moving bouncing object, and you get a positive reward for visiting the blue object up top. What's interesting is that R&D, while it's able to sometimes discover the fixed object at the top, the average heat map really shows that exploration is still fairly spread out, and we don't visit the object up top as much. And methods like R&D tend to ignore the fixed object up top and focus on the other rooms, so have trouble getting past the enemy. Lastly, we looked at this long corridor environment where we want to see, does an exploration algorithm have the patience to kind of get through this long corridor and not saturate the intrinsic reward? So here we saw, 2 out of 10 seeds succeed for ICM versus 9 out of 10 or 10 out of 10 seeds successfully find the right room object for R&D and disagreement. So that's maybe another axis of comparison among these methods. So these experiments kind of sought to isolate environmental features and compare the performance of different exploration methods. We found that some work well on things like the long corridor environment, whereas others like R&D will fail on the white noise environment. So we can already sort of start to see these methods differentiate a bit more. And for future work, we're really interested in looking at full versus partial observability.
Eric, I think we need to stop. I think we are over.
Okay.
So are there any questions? Are there any questions from anyone?
Do you have any insights why does each algorithm why does it perform like this? Like, how do you explain those graphs? For example, it seems like the disagreements always have better coverage.
Yeah, so there's a couple of hypotheses. For disagreement, for example, the fact that you have an ensemble might be why you explore walls more than objects. As you explore one room, maybe you start to disagree more, or your models start to disagree more in another room. Another feature is that the reward will never go to 0 because it's always calculated as the variance across your models. And your models are trained slightly differently in order to avoid them all converging too quickly. For things like R&D, we have insights on like the white noise environment. If you have noise with many possible states, a count-based method will have a bit more trouble. So we can sort of start to tease away these insights and see if they may be scaled to more complex environments, for example.
Thank
you. Okay, so thanks, Eric. Let's move to the next presentation.
Hi, I think that is me, Matt, and Ryan, if I'm not mistaken.
Yeah.
Daniel, are you getting the slides?
Yeah, I can do it.
Cool. All right.
Ryan, do you want to start us off?
Yep. All right. So hello, I'm Ryan. I'm here with Daniel and Matt. Our project is on neural circuit policies for multi-agent autonomous driving. So before we go into our model and our experiments, I'll first be discussing the environment. So the environment we're using, is called multi-car racing environment. It is adapted from the OpenAI GYM car racing environment. So first, the observation space, it's just a 96 by 96 by 3, just standard pixel image, RGB channels. The action space is size 3, it's continuous for steering, gas, and brake. And then we are using this in a multi-agent case. So we want to make it adversarial. So what enforces the adversarialness are two things. One is the reward structure. So as you can see on the road, there are these sort of like alternating darker gray, lighter gray tiles. And basically each time you pass one of those tiles, you get a certain reward. And that reward is scaled down by how many other agents have already passed that. So basically like the reward, like for 2 agents, you would get half the reward for a tile if the other agent already passed that tile. So you're encouraged to be there ahead of the agent. And then what is also sort of making this an adversarial case is that there is contact between the cars. The cars can hit each other. They can run each other off the road. So that's the basic environment. And then we also did some things to sort of shape the environment to test out how it affected the different emergent properties. So currently as it is, there's the reward for passing the tiles, and then there's also a standard per time step, very small reward. That way, like if you're just not moving, you don't get any reward. We have tried scaling that up and just trying out different values. We have also tried adding another like per time step reward for the grass. So if the car goes off the grass, there will be an additional penalty taken off. Because currently the only like bad thing about going onto the grass is one, you don't pass the tiles. So you don't get the points from the tiles. And then also the grass has less friction. So the car is more likely to spin out, but that didn't seem to really enforce not going onto the grass that well. So we've tried adding just this per time step penalty, and also making it, if you drive off the road, that's considered a crash condition. So the environment ends and the agent gets a large negative reward at the end. But that is the basics of the environment that we're using.
So moving on to the model architecture, which we're investigating. So it's called neural circuit policies, or NCPs. And NCPs are actually biologically inspired by the nervous systems of very small animals and have 3 main neuron layers, the inter, command, and motor. And unlike other neural networks, which generally would just have linear activations, they're actually an ordinary differential equation based on the inputs for the activation. And this is particularly useful for modeling physics-based scenarios. So NCPs have been investigated significantly in areas like autonomous driving, which are heavily physics-based. And this also allows for very few neurons to be needed because the ODE activations lead to so much more expressive power. So for example, for an autonomous lane keeping task on a real car, only a couple dozen neurons were needed, whereas several hundred would be needed with the more standard feed forward or RNN network. And for one, this leads to much more interpretable networks because you can individually interrogate how each neuron is responding to changes in the input. And also having fewer parameters is helpful if you have computing limits, such as if we wanted to turn the multi-car racing thing into actually having like RC cars racing against each other, we might not have super powerful hardware on board. So having a model with that's smaller with fewer parameters would be very helpful. Additionally, NCPs have been shown to learn the causality of a given problem better than other models.
Yeah, so to evaluate the performance of these models, we will compare them to a similarly recurrent model of basic Lstm, both of which have a prior convolutional layer to preprocess the inputs before passing it into this RNN. And both of these models will be trained or are trained using soft actor critic, which is a off-policy entropy regularized version factor critic. So kind of the layout of how we're doing this is, like I said, for these two cases, we have a convolutional layer plus our RNN, LCM, or the NCP, and that will be the actor in our training. And then in the critic case, we have a simple convolutional DQN as the critic. And so what we're actually looking for here, as we train these models, we expect performance to be as good or better than the LCM with much fewer parameters. But really what the big takeaway from using this type of model is the robustness. So prior work has shown that using noisy inputs on these different models, the NCP is much more robust and able to attend to important features in noisy inputs compared to more simpler LCM-based models. So one of the tests that we're performing is basically uncertainty quantification over the action space in a noisy input scenario. And the reason that this might be important is, for example, on a real car that this is being deployed on, one, the NCPs have the advantage of being small, so they're much better in on-hardware deployment. Then two, the noisy input robustness is good in situations such as hazardous weather and other types of scattering media that are out there. And this is the kind of the route that we're taking for this project.
So is that the end of the presentation?
Yeah.
Okay. So I have one question. So you're talking about the number of parameters. So I'm wondering, in your entire architecture, the CNN might have much more parameters than the LSTM. Right? So if I count the total number of parameters, the NCP model may not be significantly different than the LSTM model. So can you comment on what is the total number of parameters in both the models?
So both of them have a CNN network at the beginning. So both of them will have all of the parameters of the CNN. We've been trying with different CNNs. I think the current one we're using, if you give me 1 minute, the current CNN we're using.
Brian, we have these listed somewhere, right?
Oh.
Yeah, I mean, right now we have 5 convolutional layers, Yeah. So right now the CNN does have many more parameters than the NCP and LSTM.
But yeah, the LSTM model has those convolutional layers plus its own. I think we're doing a 3-layer LSTM with 256 hidden size versus the NCP right now. Ours is at 17 or 18 nodes.
Okay. Yeah, I would just encourage you to report, the total number of parameters and divide it by how much in CNN and LSTM in your final report.
No, that's a good point. So I do think that the majority of the parameters would be in the CNN, but we still, I think we'll have pretty huge savings on total number of parameters compared to the feed-forward model. Yeah, that'd be a good thing to quantify more carefully.
Are there maybe one quick question from anyone? No? So, well, thanks for your presentation. So, let's move ahead.
Okay.
Can you all see my screen?
Yeah.
Oh, sorry. Hi everyone, I'm Jia Hui, and together with my teammate Chang Qian, we did an empirical study on the active localization using deep reinforcement learning. So the active localization problem can be defined as given a map M and the agent with some sort of a perception system is then expected to come up with a sequence of actions so that it could best estimate its pose at each time step. So here's a quick system overview. The system consists of two parts, one on perception here, and the other is on planning, which I'll explain in the next few slides. So a few notes on notation. We're in a 2D grid world. This is a state space, which accounts for the coordinate as well as the orientation. And then there's the action space is the agent is expected to move left or right or straight. So for the perception module, first, what we do is to do scan matching, which is basically given our current LiDAR scan Z and the reference scan big Z from the simulator, we calculate the cosine similarity of Z with the scans at all the other possible positions and orientations. And then we do kind of a normalization to get what we call the measurement likelihood big P hat, which is of course, again, of dimension m by theta. And then we can then update the belief posterior by taking element-wise product of the likelihood P hat with the belief belt tilt xt over all of the possible grids and orientations. But note here that this belt tilt xt here is the belief coming from the transition function t, that is after the agent executes the action from its previous belief at t-1. So then in terms of the transition function, so an action will be sampled from the planning module out of the action space, which produces like a goalpost, which is ideally either would be the centroid of an adjacent cell at the same orientation or a pure rotation of delta, which is calculated here. But since no sensor is perfect, and to better approach the real world irregularity, the action and belief posterior are fed into some sort of a noisy transition function to generate the belief posterior prior for the next time step, which means that here we add a Gaussian noise and the agent will not land on exactly where it is supposed to be. So then lastly, for the planning module, we compare DRL with both dense and sparse rewards, as well as the classic active Markov localization method. So for the reward in DRL, we use the estimated belief at the true pose here. But the difference between the sparse and dense ones is defined as, instead of summing up all the reward at each time step, the sparse one will only count in the belief at the end of the episode. Then for AML, it works like the robot will virtually go one step ahead along each of the possible actions and then select one with the largest reward, which is simply the decrease in entropy here. Jiang.
Can you hear me?
Mm-hmm.
In the training session, we ran 100 episodes on each of the randomly generated maps. The agent will move 25 steps in each episode. The agent is equipped with a noisy LiDAR. The trained agent will be tested in one of the maps, but with arbitrary initial poses. Advance. Yes, here is a convergence history of two algorithms and the plots of sparse reward and the dense reward in an episode. From the convergence report, from the convergence plot, you can see that the training with both rewards converges and their performance are kind of similar. Advance. Now let's look at a few steps in a testing episode to see what's going on under the hood. The red marker on the map is ground truth, while the blue marker is the believed pose. So how did we get the believed pose? With the current true pose, the laser scan is just a corner, which is very ambiguous for robot localization. So the likelihood of pose, which is the top plot in the middle, is kind of evenly distributed over a state space. And then after Bayes filter, the posterior of robot pose is quite uncertain. The maximizer of the posterior is the believed pose, which totally deviates from the ground truth. Then the trend policy will return that the turning left action is dominating one in the action distribution, which is visibly the best action for acquiring more informative scan at once. So this is the next step. Intuitively, the laser scan could already reflect a unique pose. You can see that the posterior distribution is less uncertain and the believed pose aligns with the true pose. The policy tells us that with this scan, we should probably probably turn left at once. After turning left to step 3, the agent sees a corridor. Based on all previous scans, the belief at the true pulse has been improved to 0.13 at once. Here we make a comparison over different policies on rewards. The random policy is the purple line, which is the worst one. Both our A2C agents perform as well as the traditional non-learning based method, active Markov localization, which is the red line. It's not surprising that active Markov localization takes a longer time to make a decision, as it needs to do multiple fantasy actions and get multiple predicted likelihood functions at once. So here we summary. Basically, we trained A2C agents using existing environments, and we show that we demonstrate the efficacy of A2C agents for active localization problems, and its performance is comparable to traditional method. At once. Yeah, I think that's all. Thank you.
So one question I have is, if you were to construct an oracle, so how suboptimal is the performance of different systems? So is the active Markov localization doing as well as it is possible, or could you be doing better?
Yeah, that's a really challenging problem. If we have something like an infinite corridor scenario, I don't think a active Markov localization can perform pretty well, because essentially AML is with only the horizon is just one, so it's basically greedy strategy. So yeah, it cannot plan ahead for a long time. So I think long corridor will be challenging. Did I answer your question?
I mean, kind of, but I guess I can ask in more detail offline. So, and what's the relationship between the reward and how fast you localize? Is there a one-to-one mapping? Because the reward seem to be the probability of the belief probability.
Right.
But I guess you also care about how quickly you end up finding states with high belief. So do you account for that also somehow?
We didn't explicitly account for that, but you can read it from this reward plot. You can see that with dense reward, which is the light green, the blue one, you can see that the reward curve increases faster than others. So because it uses dense reward, so rewards at initial steps will also be counted in training. So I think, yeah, so it's implicitly accounted, I think.
Okay. Any more quick questions from anyone?
Well, why do you choose this environment? It seems like in this environment, the IO policy only performs a little bit better than random policy.
Yeah, so you mean the performance improvement is not so considerable, right? I think I admit that the environment is kind of simple. If we increase the number of grids, so right now it's 11 by 11 maze map. If we make the environment more complicated, I guess the performance of RL will be much better, I think.
I think the performance we're both speaking about the accuracy as well as the computation time. But if you think about AML, basically you're doing scan matching of every possible action you have. So once your environment gets super complex and you do scan, the time you'll be spending on scan matching will be huge. But for DRL, basically you still fit the same thing into the neural network and you come up with an action. So I think probably DRL will be better in more complex environments.
Okay, I think we should stop here, but if you have time, it would be great to see that. If you have time to include, maybe a bigger map, or if your computational resources allow for it. Yeah, but let's thank the speakers and move to the next team.
Hi, everybody. I'm Jacob, and I'll be doing advanced imitation learning in Vista. So Vista is virtual image synthesis and transformation. It's an autonomous vehicle driving simulator that's supposed to be photorealistic. So basically the way this environment works is you collect human trajectories following the center of a road, and then you can use 3D camera homography to essentially create synthesized views from different viewpoints along the same road. So if we take this like original image, we can project the pictures out into like a 3D space and then do ray tracing back into these like alternate positions. You can see like what this looks like on various different like rotations or translations. And so this is great and is like fairly photorealistic, but the problem is that it requires a fair amount of computational time. So the original authors present experiments using reinforcement learning, but their reinforcement learning approaches take a lot of like on-the-wall clock time. So we want to be able to leverage expert examples in order to reduce like the total training time. So these are kind of the baselines that we're working with. So just initialized networks on the left column have like, of course, very poor performance. So performance in this is measured as like average reward over 10 episodes, where reward is equal to like 1 + 1 per step. So effectively measuring like reward or like total time steps survived without crashing. So initialized networks, just to get a baseline of what like absolutely no training can do, is about 3 steps. Then vanilla policy gradient, what the authors originally presented, I could only get to train to about like 48 steps without crashing. And then I ran PPO as another baseline and got about 320 as like the baseline average for what we're like the algorithms we'll be looking at. So now I move into kind of 3 advanced imitation learning algorithms. So starting with behavior cloning, then Dagger, and then into Gale. So behavior cloning was first for driving, was first proposed in like the Alvin architecture in late 1980s. And so on the x-axis, I'm showing the order of magnitude of expert examples. So 10, 100, 1,000, and 10,000. Like I wish I could have run with more expert examples, but I'm kind of limited compute-wise on my laptop. So just pure behavior cloning, we were able to get like decent performance relative to the PPO baseline with like the 10 to the 4th number of examples like almost equaling out in performance. And I ran the like Dagger algorithm. This is interesting as I had to essentially create like a suboptimal controller because the environment only has optimal examples for when the agent and the expert are in the exact same position. So effectively, I made a controller based on the like relative position of the agent to like the expert. And so if we'd been able to make an optimal controller, like maybe these results would have been stronger. But we know that like from our p-sets that we can still receive like reasonable function from a suboptimal controller. And again, so the like 10 to the 1 and 10 to the 2 number of examples aren't finding like that good of performance, but the 10 to the 4 performance almost matches the like results of PPO. Then I tried out Gale. So Gale is generative adversarial imitation learning. It's basically functioning using like the GAN objective to find like a saddle point between a policy and a discriminator. So the idea is that like the discriminator tries to identify samples that came from either like the expert or the policy. And then the policy tries to then create like state action pairs that are like difficult for the discriminator to judge as like real or fake. So Gale actually worked like much worse than the other algorithms until we reached like a large enough kind of threshold of expert examples. So as you can see in the graph, like until we reached that like 10,000 example point, Gale was performing extremely poorly. And I think this has to do with the fact that like with Gale, you're effectively training 2 networks, like the discriminator as well as the like policy. And so I think there's just kind of like an increased demand for expert examples. So next, on top of Dagger and Gale, I also tried pre-training with behavior cloning, just because like with Dagger, if you're exploring with a random policy that maybe also isn't efficiently using like your limited number of expert examples. And then likewise with Gale, if we have like a pre-trained policy, then maybe we can like get more advanced training like more quickly. So on the left, the Dagger, so in green, we have the results of pre-training with behavior cloning. So we definitely see like an increased performance with fewer expert examples, but it still does kind of appear to be reaching a similar point in like the 10 to the 4 case. And then a similar performance in the behavior cloning pre-training for Gale. We see that it kind of pops up before the original Gale does at like 10 to 10 to the 3 examples. And then it's still interesting to me that like at 10 to the 4, they seem to kind of come back to the same point. So here's a comparison.
So Jacob, there's a clarification on the plots. Can you go back to the previous slide? So when you say BC plus Dagger, what do you mean? Do you mean you pre-train just with BC and then do Dagger?
Yep. So in both cases, pre-training with like the x-axis number of expert examples with behavior cloning, and then beginning the either Dagger or Gale.
So then so when you're plotting the number of examples, is it all the examples you use for pre-training and fine-tuning?
So effectively, I said that this is technically like 2 times the order of magnitude. So for example, in like the 10 to the 2 case, like right here, this is effectively like 2 times 10 to the 2. But since I was like plotting an order of magnitude, I decided to like omit the factor of 2. So like in the 10 to the 2 case, I use like 10 to the 2 for behavior cloning, and then a different 10 to the 2 like Oracle labeled examples for Dagger. Does that make sense?
Yes, it makes sense. I think just for accuracy, I would encourage you to plot just the total number of examples over here so that the plots are comparable. Okay.
And then, so in the comparison of all methods, we can see like pretty clearly the behavior cloning like pre-training approach is very helpful. One like problem is that I am in like kind of a compute like limited environment with just my laptop. And so like it would have been great to run these models, especially the like PPO baseline for like far longer or with like larger networks. So that's kind of in terms of like future work would be to like run these models again with like 10 to the 5, 10 to the 6 examples, or like just like far more PPO like training epochs. But I think this kind of also goes to show that like data scarcity or compute constraint kind of makes like algorithmic use of examples more important. So I have like references and questions.
Any questions from anyone?
How are the expert trajectories generated? Are they from the PPO policy?
So the expert trajectories are from the original expert driver. So the way the data is originally collected is like you can break this up into like we have a delta t of like 0.3 seconds. So at every 0.3 seconds, like an image is taken alongside the like steering wheel curvature that the original expert driver took. And that's both used to create the simulation as well as used as the expert examples for like the training algorithms.
So these are coming from a human who drove the vehicle, right? Is that correct?
Yes.
Okay. And for Dagger, you constructed a suboptimal expert on your own, or what was the suboptimal expert that was constructed?
So given like a simulation step, we know the like delta x and delta y and delta theta that represents the agent's different location from like the closest expert location. So that's how we can construct the synthesized image. But then using like those 3 like differences alongside the expert action that was taken, we can come up with a controller that I ended up using like the product of the delta x and the square of the expert action. That creates a controller that doesn't crash. It is like fairly wobbly. And so that's maybe also an opportunity for future work. But if I had like a perfect controller, that would just be like solving the self-driving problem.
Okay. Thank you, Jacob. So we'll move on to the next presentation.
Hello. Cool. Let me share my screen. Hi, everyone. I'm Bryce, and I worked with Gregory on comparing methods of credit assignment used to train policies, model-free policies. Okay. First of all, let's just talk briefly about what credit assignment is. It's basically this idea of given some trajectory, we can like take one time step where we took an action A at some state X, and we want to basically like decide how much this action A affected the return of the entire trajectory. And you'll notice that this is kind of like, this is not a super new idea. This is what we've been doing in most of our policy learning, where we use proxies for the influence of action A to predict the return. But we'll see that there are shortcomings. For example, in the Dorky environment, if we think, intuitively which actions are impactful to the return, obviously we want to reach the goal tile, but to do that, we would need to like pick up the key and then bring the key to the door, and then we can go to the goal tile. And the problem is that with the first two, the environment doesn't give us any explicit reward for doing these things. So it's not obvious to the algorithm that these actions are like conducive to earning a high reward. And so basically, a few ideas that we use to like get around this are things like temporal difference, where we basically discount our reward and we try to basically predict this discounted reward over like some infinite horizon. And this works well. It worked for the Dorky environment, but ultimately, like in the general case, it does suffer from this sort of vanishing reward, where the further away the longer range our interaction is, the worse off it is at predicting it, because the reward simply vanishes exponentially. And moreover, like intuitively, time isn't a relevant factor when we're trying to maximize reward in these environments where we just earn a flat reward for reaching an objective. So this is kind of a hackneyed solution when we think about it. And the other idea where we basically just sample many trajectories and then we try to sort of average them and take actions which occur more in like high reward trajectories. And again, it works well in simple environments, but in more complex environments, we see these very high variance outcomes where super sparse rewards will only occur like once in very, very few trajectories. And so we don't end up learning very stable policies.
All right, well, one of the approaches that we have considered from a research paper was the idea of hindsight conditional assignment. This is basically the idea of normally we have policies that decide an action given the current state. The idea of a hindsight conditional assignment is that we complete the trajectory and then we want to figure out the probabilities of certain actions, conditional on both the state and a function of the completed trajectory. The paper that we had found basically demonstrated two hypothetical functions of the trajectory, which are state conditional, in which the function is a future state, and return conditional, in which the function is a future return. Now, obviously, because this is hindsight, we aren't able to figure out this distribution as we go or sample it. And so the paper that we have found basically resolves this by using importance sampling, where we sample by the normal trajectory, and then in order to compute returns and other expected functions for policy gradient, we take the ratio of this to the original, as you can see on the calculation of the Q function right there. And so this is basically the idea of it. And what we've done with our experiments is to try to implement these. So, and what's interesting is that when we've actually tried to implement this, HCA state doesn't perform very well at all. In fact, it actually performed quite terribly enough that we had to use another implementation just to confirm that it wasn't performing well, because we thought ours had bugs. So there's actually, and it's not just in returns, it's actually extremely slow, because the thing is that we aren't able to have any other way of learning this hindsight policy except by using another neural network which takes in the two pairs and then tries to learn this distribution. And it's extremely slow because for a trajectory of about 250 steps for the Dorkey environment, we have to choose pairs in order to train this distribution. And 250 choose 2 is 3,111.25. So it's a very large number. And the thing is that out of all of these pairs, only a very few amount of these distributions are significant, such as those involving picking up the key, going through the door. And that's on trajectories in which the agent is actually successful in accomplishing the task. Most of the time, and especially in the beginning, the agent is unable to accomplish this task. And so most of these events are not of significance. And so the distribution is unable to learn well. And because the rest of the system depends on learning the distribution, it's not able to learn well ergo. And so below you see what actually, when we examine the paper, are a lot of the very toy examples that the paper used to demonstrate success of their HCA algorithm. And as you can see, they basically involve a lot of very simple discrete Markov's agents with very few amounts of actions between. So this is nowhere in comparison to the Dorkey environment, which has tons of states and tons of actions that you can do at several times. All right. And as you can see, this is basically our return for this HCA state, just to kind of show that it's not particularly great at performing. All right, but how about HCA return? This actually tends to perform a lot better in comparison, likely because the distribution is much smaller and the only possible rewards are between a 0 for no success and then 1 for certain success. So it's likely that the distribution that you learn basically needs a lot less data to sufficiently train and then master. And then as you can see between here and the right, this is a comparison between HCA return and then current PPO algorithm. So HCA is somewhat decent. We, in the Dorkey environment experiments, it's, we can compare.
We need to wrap up. We need to wrap up in 30 seconds.
All right. Okay, all right, next.
Okay, I'll just speed around the rest of this. Basically, we also tried another algorithm called Rudder. The general idea is we want to basically just move all of the expected future rewards into the present. And so we can immediately predict how good our actions are. And basically, it kind of compensates by like removing the Markov assumption of how our rewards are given from the environment, so that we rely on many past states to determine our current reward. How it compared to our baselines was we didn't really see a significant decrease in complexity. We think maybe the environment was the cause, or maybe maybe certain conditions would be more conducive for Rudder improving. And also Rudder demonstrated a lot of computational slowdown because you have to basically ingest all of the states in a trajectory into like some kind of recurrent structure.
And our project is still ongoing. We have a set of objectives to continue, such as examining other networks, and then basically just, comparing and gathering metrics. So that's what we have currently. So we have time for questions.
So did you ever try evaluating HCA on the environments which are there in the paper, just to make sure the implementation is correct?
We haven't currently. They don't specify exactly the structure of their environments besides abstract Markov structure. So
Rudder does posit a specific environment, but I don't think there's actually an implementation that lives somewhere. So it seems like a theoretical kind of.
I see. I mean, you might just try one of those theoretical environments. It will be very simple to just build up and just see if it is working better, at least on those environments. Yeah, but I think we're running out of time. I mean, we could discuss it, in the office hours if you want to. But let's move on to the next presentation for now.
Hi, I'll just share screen.
Yeah.
Can you? Can you see my screen?
Yeah.
Okay. Hi. So I'm Ayush. This is my course presentation for. So basically, I'm proposing a variant of the soft actor critic algorithm called SARC, which is soft actor retrospective critic. And so the premise is that over the last few years, various techniques have been introduced to improve gradient estimates and actor critic methods. Broadly, we can segregate these methods into two types. There is PPO, TRPO, DDPG, A3C, and an entire family of methods which propose various heuristics to improve actor learning for better convergence. And then there is also SSE TD3, which advanced performance by improving critic learning. Primarily, both of these methods relied on using two critic networks. And apart from that, TD3 also updates the critic twice as frequently as the actor, and SSE used an entropy regularizer. So the hypothesis that I work with is that since gradient estimates depend upon the critic, and improving critic resulted in significant performance improvement, can accelerating the critic convergence provide a better gradient estimate for the actor? So sort of the motivation is that there is a two timescale nature to the way actor critic algorithms function. So there is a critic and there is an actor, and sort of the actor is always dependent upon the estimate of the critic for convergence. So if the critic, sort of if the convergence of the critic is accelerated, then a better estimate of the value from the critic can result in better policy gradients for the actor. So to achieve this hypothesis, the proposition is that I augment SSE critic learning with a regularizer to accelerate convergence and achieve better policy gradient estimates. To do this, I adapt something called the retrospective loss, which I introduced in the paper in last year in KTD, which we show is an equivalence of a standard fixed point theorem. And through extensive experiments in various supervised learning setups, showed that it can accelerate convergence across a bunch of tasks for supervised learning. So as a preliminary, the retrospective loss it's a very simple, easy to implement function, just takes around 5 lines of code, no hyperparameter tuning. And the goal was that it is a local non-stationary adaptive function, which seeks to enforce the following constraint: that when training a deep neural network on a supervised learning task, the predictions at any training step T should be enforced to be closer to the ground truth than to the predictions at a previous training step TP, where any TP is less than T, and it is always at some sort of a lag with respect to T. So considering a DNN model G, which is parameterized by theta and on a training data set, we can represent theta T to indicate the parameter state at any iteration T, and theta star could be the optimal parameter state. We don't really have theta star, but we do have G of theta star, which is the ground truth label. Then this is basically the definition of the retrospective loss, which says that the prediction at my current training step should be more closer to the ground truth than to the prediction at a previous training step. And it is basically governed by these following parameters. There is theta T, which is the parameter state at the current iteration. There is theta TP, which is the parameter from a previous iteration. And then there is this retrospective delay, which is the distance between my current state and the previous state. And it is always lies between F and 2F minus 1, where we could say that F is the retrospective update frequency. And we also have K, which is sort of a scaling margin, which sort of we call the retrospective margin. And then in the previous paper, we primarily use L1 norm as the distance metric. So the SARC definition is very straightforward. We simply extend SSE by augmenting the training objective of the critic network with the retrospective loss. So basically, SSE has two critic networks. So for both of the critic networks, we take the standard SSE loss, which is the MSE loss plus entropy, and just add the retrospective loss. So for experiments, I conducted experiments with PyBullet and various environments from PyBullet and Deepmind control suite. And all results are reported as mean and standard deviation over 5 seeds, each trained for 2 million steps. For baselines, report performance comparison with SSE, TD3, and DDPG. I'm following the implementation from the spinning up repository. And the interesting thing, which was also one of the motivations for me in the work, was that the goal is to minimize parameter tuning. So hyperparameters for all experiments are default as given in the spinning up repository. So I do not change anything. And for the retrospective loss, I basically do not do any parameter tuning. So all the results that I see, all the gain that I get is without ever tuning any parameters. So parameter tuning may give some benefits, but like even without parameter tuning, we can get significant benefit. So that's sort of one of the things that I'm trying to advocate. So the first set of results that we get is on the pi-bullet environment. So I conducted experiments on 5 pi-bullet environments, training for 2 million steps. So these are basically the plots. This is basically comparing SSE with SARC here. And I would say that on 3 of the 5 environments, SARC significantly outperforms SSE, which is Ant, Half Cheetah, and Walker. Like, sorry for the typo, it's Walker here. And on Hopper, SSE is slightly better, is better on average. And on Reacher, both are competitive, but yeah, SARC got significantly better performance on 3 of the 5 environments. Then next, I did experiments on the Deepmind control suite. Now here I'm comparing performance with TD3, DDPG, SSE, and SARC on 6 Deepmind control suite environments, all trained for 2 million steps. And I would say that on 5 of the 6 environments, SARC achieves state-of-the-art performance and it significantly outperforms SSE or is competitive with SSE on almost all of them. And only on the Cheetah Run environment, it did not get better performance than TD3 and DDPG. So these are basically the plots. So I would say that on 5 of the 6 environments, except Cheetah Run. So for reference, red is SARC, green is SSE, blue is DDPG, and purple is TD3. So on 5 of the 6 environments, all except Cheetah Run, SARC is highly competitive and it's significantly better than SSE and highly competitive with both TD3 and DDPG. And even in cases, for example, in Walker Run, where we see that SSE gets competitive towards the end, SARC gets a higher reward much faster and has significantly lower variance. For example, on Walker Walk, the variance for DDPG and TD3 both is very high. So we have like significantly lower variance and competitive performance. And as an ablation study, we've realized like during the course projects and the assignments that performance is often strongly coupled with the network architecture. So as an ablation study, I try to increase the complexity of the actor-critic network, basically increasing dimension of the hidden size, following like the discussion in this paper called Deep RL That Matters, which came out a couple of years back, which also discussed this aspect. So by increasing the complexity of the network size, again see that there is significant performance gain by SARC against SSE on like a bunch of environments across pi-bullet and Deepmind control suite. Yeah. So this is the conclusion that SARC consistently outperforms SSE on experiments with very limited parameter tuning and is also competitive with other state-of-the-art methods. And an interesting direction of future work is to see, can the retrospective constraint be generally useful in reinforcement learning beyond SARC, such as like with other actor-critic methods or in offline RL and some of the other constraints. And another direction that I'm actively thinking about is if I could have like a stronger theoretical intuition on why this really works. So I've been doing some investigation. So, and yeah, that's like a direction of future work. Thank you.
Any questions from anyone? No. So I would recommend just including the variance numbers in the tables that you have. That would really help in comparison. The other question I have was, so you're imposing this retrospective loss and you have some time period T, right? In which you do the retrospective. So does it really matter how long is the time window? I mean, could it be 1 or 2, or does it really need to be long?
Okay, sorry. So I think I like to sort of be careful for time. I think I went a bit too fast. I can just go back. So basically, it's not a time window. It's like it's applied all throughout the training process.
Oh, I see.
And
okay.
The lag is between what characterizes my current model and the previous model.
I see. Okay. Okay. So
It's like we have a, yeah, we
okay.
have like the moving previous model, which is updated after every time window frequency, which is like.
Cool. Cool. Yeah, I think it would be good to see what happens with the overestimation bias.
Yeah. So
I think maybe even some toy experiments showing it for, we can consider environments for which you know the ground truth critic.
Yeah.
Then you can show that you converge faster to the ground truth critic.
Yeah. So I have a couple of extra results which I did not put in the slide because like they were not formal yet. But like I did, so it's like the idea is that if you have to accelerate convergence of the critic, you could either use explicit acceleration techniques or you could update it more frequently, as TD3 is doing. So I did try doing that, like updated the critic twice as frequently. And like that's very interesting. So on some environments, it does improve with respect to standard SSE, but still like it does not get as well as XR. And on some environments, just updating the critic more frequently did not improve performance at all. So like that was another thing that I saw. And yeah, I mean, I can probably like discuss it offline, but yeah, so here I was like trying to just, okay, I can probably like, for sake of time, I'll just discuss it offline.
Cool. Cool. Well, thanks, Payush, and thanks everyone who presented. And I think looking forward to all the presentations on Thursday. And with that, we'll close the class, but it's also my office hours. So, people who are interested can stay back. Otherwise, the class is officially closed.